This class is intended to prepare people that make, measure, and model materials to work in the field of quantum information science. It's the kind of setting the stage, setting the platform so that you can get more advanced training. Okay, so we're going to start at the very beginning because that's a very good place to start, as they say. All right, so when we think about quantum information science and engineering, it really encompasses a lot of different areas, including computing, sensing, communication, cryptography. And at the heart of all of those technologies is the thing we call the qubit, or quantum bit. And to understand what a qubit is, it really helps to come back to what a bit is. So what's a bit? Yeah? Mm-hmm. Yeah, so it's a binary digit. Typically, we think of it as 0 or 1, true or false, on or off, plus or minus. And it is a representation of the logical state and the correspondence between those values, 0 and 1, and the physical state of the underlying system is dependent on how the computer is programmed. So that's kind of up to the programmer to say what the 0 and 1 represent. And so we can draw an analogy or contrast between this classical bit, which stores information in a computer, and a simple light switch. So the light is either on or off. Forget the dimming lights. It's not dependent on me being in the room to observe it. So 0 or 1. The light is on or off. All right, so what about this quantum bit? So that's the qubit. So let's consider the light switch again. A quantum light switch could be represented by a sphere like I have drawn on the right here, with the north pole being off and the south pole being on. And imagine I'm going to put this special light switch in a room that's separate from the light, and I'm going to control the switch by putting my finger somewhere on the sphere. So I'm in the room with the light switch, and the light is in a different room. If I put my finger on the north pole, the light will definitely be off. And if I put my finger on the south pole, the light is definitely on. You can go to the room and check. That's always going to be the case. But if I move my finger anywhere else on this sphere, the light might be on or off. And when you check, you'll know whether it's on or off. If you don't check, the light is in some indeterminate state. It's not dimmed. It just exists with some probability of being on or off when seen. So if I put my finger here, I'm in an indeterminate state. So some probability of being on or off. As soon as I walk into the room and I check, the light is on or off. The act of me going into the room and checking it out forced it to be that way. And this quantum light switch that we've created is an example of a two-state quantum system. All right, so quantum bit, the qubit that we're going to be talking about, is another example of a two-state quantum system. And it's the basic information unit in quantum computing. So with the qubit, we're going to replace our on and off on our quantum light switch that we just created with two states that we call 0 and 1. The north pole is usually referred to as 0, and the south pole is usually referred to as 1. And these kets that I've drawn just represent those quantum states. And the important point about a qubit versus a classical bit is that it can be in a state other than 0 or 1. It's possible to form linear combinations of those states, and we call those superpositions. So the state of my qubit is equal to some coefficient alpha times 0 plus some coefficient beta times 1. So we're here, this is the state of my qubit. So we cannot examine a qubit to determine its quantum state. We can't determine alpha and beta. Instead, quantum mechanics tells us that we can only learn something that's kind of more restricted about this qubit. When we measure it, we get either 0 with a probability alpha squared, or we get 1 with probability beta squared. And there's a normalization sort of requirement. The probabilities have to sum to 1. So we do know that alpha squared plus beta squared is equal to 1. So this kind of dichotomy between the unobservable state of the qubit and the observations that we make is really at the heart of quantum mechanics and quantum computation and quantum information. It makes it hard to intuit the behavior of this quantum system, but there's an indirect correspondence between the qubit states, and we can indirect correspondence between the qubit states, and they can be manipulated and transformed in ways that lead to measurement outcomes that depend on the different properties of those states. So a single qubit by itself, not so interesting, because it is, when you observe it, either going to be on or off. But when it starts interacting with other qubits, the state that it was in before it was measured is going to influence what happens with the other qubits. And it's the whole system that allows you to kind of get more out of it than what you observe when you observe it. Yeah, so the systems, these quantum systems have real experimentally observable consequences.